So we are coming now to a very important chapter, that's energy storage. During nighttime we don't have any photovoltaic energy, and if you want to supply energy during 24 hours, you have to think about storage. So we first talk about the storage parameter and characteristica, the storage technologies. We start with the mechanical storage, pumped hydro storage plant, and compressed air storage. We don't want to discuss about flywheels because they provide power only for a very short time. We will then talk about chemical storage. Actually, this will be the main chapter. Hydrogen storage, power to gas, the traditional lead-acid battery, and the newer lithium-ion batteries. Then we talk a little bit about electrical storage, basically high-capacity capacitors, double-layer capacitors, so-called supercaps or ultracaps. And at the end of this lecture, we will talk about storage technologies in overview. Let's start with the storage characteristica and the parameters involved. So we have efficiency. So the efficiency is a ratio of actual energy output towards energy supplied. The power indicates the maximum quantity of power to be supplied by the storage system. It's expressed in watts or kilowatt or megawatt or even gigawatts. Then we have the storage capacity, one of the most important parameters. So it's electrical energy in kilowatt hours or megawatt hours or gigawatt hours inside the storage as a whole, or only the usable amount, which is usually better. But you should check if you guys find something in the data sheet, whether it's net energy, so the usable energy, or whether it's energy supplied for the charge, and so you have to think about the losses and some remaining part that has to stay in the batteries. The storage capacity is essential for the storage layout and thus defines the actual cost of energy storage. Energy density, so the energy density in kilowatt hours per cubic meter or kilowatt hours per kilogram describes the ratio of the usable amount of energy to the volume or the mass of the storage system. That's not so relevant for a stationary system, but more if you think about transportation. So for cars, trains, or buses, this becomes very relevant. So the further parameter is a charge and discharge time. Measured in seconds is a period of time in which a storage system can absorb or deliver a certain amount of energy in percent of the storage capacity. So for some technology that's not a problem, but some technology they need a certain amount of time and they have some certain limits. It could extend from seconds can even be usable for primary power control to several days to balance out medium-term electrical storage. Another important parameter is the self-discharge rate. So some storage system lose energy even in standby mode. Self-discharge rate is given in a percent per unit of time. So for example, percent per month. But if you have, for example, capacitors, it's more in a percent per hour. Reasons for self-discharge can be a leakage current, heat losses, magnetic currents, or, for example, if you see the pumped hydropower plants, evaporation. Storage cycle number, this is very, very relevant for the costs. Sometimes it's discarded, so people just give the investments costs, but if you compare different systems, you really have to know the storage cycle number and under which conditions you achieve this number of storage cycle. I will discuss a little bit later. So the storage cycle number indicates the maximum number of 100% charge and discharge cycles, so-called full cycles. During the lifetime of storage devices, lifetime is usually defined as the threshold when the storage system reaches below 80% of its initial storage capacity. This is quite interesting to know. So there's sometimes in the discussion of a second life of batteries, for example, car batteries for electrical vehicles, that they get exchanged after they reach below 80% of their initial capacity, but they are still usable, for example, for stationary applications. The useful life of a storage battery depends greatly on the usage profile, so the depth of discharge, the rate of charge and discharge, and operation temperature. As I told, we'll discuss it in detail a bit later. The specific costs. The costs of an energy cycle, so in euro per kilowatt hour, including investments costs, storage cycle numbers, and losses. We'll discuss this also in detail, also in the exercise. So we now go to the storage technologies. So we have different storage technologies. We start with the mechanical storage. So this could be a flywheel, pumped hydro storage, or compressed air storage. Chemical storages could be the typical batteries, lead-acid batteries, lithium-ion batteries, or nickel-cadmium batteries, or hydrogen or methane. Electrical storage, for example, double-layer capacitors. Let's start with the pumped hydro storage power plant. These are also the storage devices today which offer the most installed capacity. So the principle is quite simple. So they are usually hydropower plant, and they have an upper reservoir where water is stored and can be released to the lower reservoir. During periods of high electricity demands, the stored water is released through turbines and can produce electricity. So we can equilibrate or balance out fluctuations and so on. That kind of power plant is often disrupted while we may lead. Yes, you have to consider nature invention. I come to this also a bit later when we see some examples, because they are large flooded areas. We'll show the example of the power plant Itaipu in Brazil, which flooded about 1,000 square kilometers of area. So the electrical working capacity of a storage power plant is given by what you see here, the volume times the density of the media. So this is water, and then the acceleration gravity, the gravity acceleration, the height, and the combined efficiencies. So here we have efficiency. This is a volume again, the acceleration due to gravity, and the height of fall, and the combined conversion efficiency of first T is for tubes, second T is for turbine, and G is for generator. Can also go one step further and not only use a natural reservoir, you can actively pump up water. This we saw before. And yes, the electrical power of a pumped hydropower storage is given by the derivation to time. So E, what you see here, E dot, it means we derivate it 2 times. So we have the power, the energy derivative times power, and then we have the density stays constant, G stays constant, H stays constant, efficiency stays constant. So we have here the derivation of the volume. And as you see here, and this efficiency, the efficiency may reach 80%. And here this is a volume flow, or if you could be also translated into mass flow if you consider the density. So we take such an example. In Austria, there's a big artificial lake built in Kaprun. Some people know it from skiing there, and it's quite high up, about 2,000 meters above sea level. The data, which is you see a cross section here, this is a bit in German, but translated for you. So the upper storage limit, which you see here, Stauziel, is 2036 meters. Then we have the lower limit here. This is the amplitude we will use for our storage, and this is in a height of 1,960 meters above sea level. The outlet is much lower. It's not visible here. It goes here below that, and this is at 1,672 meters above sea level. The storage limit, or the volume you can use, is 85 million cubic meter, or 85 billion liters. So the area relevant for the rain collection, so the water has to come from there, and usually smaller rivers collect this rainwater, and the rivers within an area of 94 square kilometers go to this lake, and so you have a collecting area of 94 square kilometers. The precipitation is a dot, so the change in height, so it's 2 meters per year. Usually you find also the precipitation in millimeters, so it's about equivalent to 2,000 millimeters per year of precipitation, to either rain or in this height often snow. So if we have all the data, so we can calculate the volume flow here. So we have the precipitation area of 2 meters per year, or 2,000 milliliters per year. We have the collecting area, 94 square kilometers, or 94 million square meters. And so we have here yearly flow of 188 million cubic meter per year. This is about twice the storage volume, so we have here 85 million cubic meter. So we just take it for granted that the reservoir has a cuboid layout, so we can use the average height, which makes calculations much easier. So we have here the average, the arithmetic media with two heights here, and so this is the upper limit, this is a lower limit, and this is the total height here, this is the outlet height, so we have a total usable height of 300, relevant for the potential of 326 meters. The average energy content is mgh in average with this dash here over there, and you have here a rho times volumes times g times 8 dash, and with the water density, which is typically 1,000 kilogram per cubic meter, and the acceleration of gravity of 9.81 meter per second in square. And so the energy is just if you apply all this, you have here 272 times to a power of 12 watt seconds, or if you put it in hours, 76 billion watt hours. So we can calculate the average power of storage over 1 year. So that is here just the number of hours during 1 year is 8,760. So if we divide this, and so we have in average constantly 8.6 megawatts. That type of operation is not very useful. Usually the reservoir lake is filled up in summer by the melting of the snow, and it emptied during winter for maximum load. The annual turnaround is about twice of the reservoir volume. At a full load operation during 25 years, the power of the turbine is dimensioned as here 69 megawatts. So this is here the annual turnaround, twice the reservoir, so twice, and then 25% of the year. So it's divided, multiplied by 4, and then we have this 69 megawatts. As I mentioned already, you have to should take care on the natural impacts of such a power plant here. And here you see Itaipu. You see this height of the dam. This is actually almost 200 meters high. So it's a really gigantic plant here. Was for a long time. It's from the 80s until year 2000, until to the Three Gorges Dam in China. This has been the largest, not only hydropower plant, this has been the largest power plant on the planet. And the lake area created by this plant is from 820, depending on the time of year and so on, up to 1,400 square kilometers. So on average, as I mentioned before, about 1,000 square kilometers are flooded to the construction of that hydropower plant. The outlet drain is 14,000 cubic meters per second. Here you see just a cross section of that. So you have here the inlet here, and then the outlet to the turbines. So we have here the turbines here. These are 19 turbines, each in the vicinity of 1 gigawatt, and so the maximum power to be generated is 19 gigawatt. Not all of them are used, so theoretically now it's power in the vicinity of 14 gigawatt, and this generates an electrical energy of 93,428 gigawatt hours per year, or 93 terawatt hours. To put this in relation, about the German electricity consumption per day is about 1.5 terawatt hours per day. With the years, about 600. So the pumped hydro storage plant, so you just, as I mentioned before, you actually pump the water up to the upper reservoir, and during periods of high electricity demands, the stored water is released, as in the conventional storage hydropower plants, and you produce electricity. So if you have a lower reservoir and upper reservoir, and here you have a combined pump and turbine. This is only possible with the Francis turbine. If you use different kinds of turbine, for example, Pelton or Kaplan turbine, you have to have a separate turbine and a separate pump. So here, so the amount of electricity that can be stored, this depends on the turbine and the generator technology, the size of the upper reservoir, and the height difference between the upper and lower reservoir. So this kind of power plants need about 1 to 3 minutes before full power becomes available. So then it depends on the size of the upper reservoir, but quite typically are 8 hours of reservoir storage, depending. So, for example, in Norway, there are reservoirs which are much bigger, so they can supply energy for even weeks or months. Although short-term power fluctuation cannot be compensated directly with a couple of seconds, pumped storage power plants are still much faster than any conventional power plant. So the fastest conventional power plants are gas power plants. They need about 8 minutes. The most modern ones, 5 minutes only. If you take a look at coal power plants, lignite power plants, they take up to 8 hours to come to full power or to be throttled. So they have a rapid start capability, so they can be used to smooth the residual load. They can be used to compensate for unexpected variation in power consumption. They can provide also control in the energy market. And Germany now, we have currently about 30 pumped hydro storage power plants, which have together a power of 6.2 gigawatts. And Many devices are small, they have a power of less than 300 gigawatt. The most powerful pumped storage power plants in Germany is about 1 gigawatt and a storage capacity of about 8.48 gigawatt hours, and it's located in Goldistal. I show you some pictures about that later. So this is just the principle here. You have here the lower reservoir and the upper reservoir. You have the turbines, and during time of low demand, and usually if you have low demand, you have low electricity prices. So you take that advantage and pump water up to the upper reservoir. If there's high demand, usually also prices go up, and then you release that water from the upper reservoir through the turbines and generate electricity and make even profit if the price difference is high enough. This price difference is a bit of a problem in Germany. So if you want to use 100% of renewable energy, and that's in Germany basically solar and wind power, we have to have storage and compensation mechanisms to balance out the power availabilities during day and night and during periods of high wind and low wind. These devices are very useful, but the moment, due to the low flexibility of conventional power plants or existing conventional power plants, electricity prices are really, really low, sometimes even negative, because the conventional power plants, for example, lignite power plants, can't react sufficiently fast enough. So from the point of the investor who wants to invest in such a power plant, it's rather difficult, because okay, he has low electricity prices, so he can pump up for cheap prices, but during high demand, the electricity prices are not sufficiently high to make such a system profitable. So here, close by to Paderborn in Höxter, there was a very well advanced plan of such a power plant, but it couldn't be realized because the business plan didn't work out, because the price difference between pumping and releasing hasn't been big enough to justify an investment. Here you see a power plant operating in the south of Germany, Säckingen. It's a quite interesting power plant. It works in a cavern, so you don't see anything of this power plant. And here you see the pumping here of the, so this purchase electricity in nighttime and release it here during daytime. And usually this should be enough to justify the investment cost. So it works profitably during that period. Here there's a picture of that. So here you have the turbine and pump, so quite a big device here. And as I mentioned before in the scheme, you pump up water and release it during daytime. So this is not a Francis turbine, so you have two different turbine and pump separated here. So advantages of such pumped storage power plants are they provide system security and presently, but even more important for future NSC systems. They are also considered as a long-term energy storage because the losses by water evaporation are quite negligible. So this can be even used for seasonal storage, not only for daily or weekly storage. There's another example here on Ireland. So you see here the upper reservoir, and here the intake, and here the power plants and the discharge. What you see here, usually the power plant is a little bit lower located than the actual discharge. If you would locate it higher, there could be quite a low pressure here, and this could lead to a kind of vacuum bubbles or to some bubbles in the turbine, and there is an effect called cavitation, and these bubbles or steam bubbles can destroy the turbine blades, and therefore you always put the discharge a bit higher, so there is a counter pressure also on the outlet of the turbine, and this avoids this cavitation issue. Here is the Goldistal power plant. So same thing, so the outlet is here a bit higher to put some counter pressure, and here we have the cavern where all the equipment is here, the turbines and the generators and the pumps. Here the height difference here is in between, depending on the height of the upper reservoir, between 325 and 280 meters. The this size is only 29.5 meters, so the height of the upper reservoir, the internal height, and the volume here is 12 million cubic meters. And here you have the sizes and show you some pictures here. So this is a lower reservoir. It was formerly a river, but there was a dam built just to have a bigger size of the lower reservoir. And this is a total artificial upper reservoir. As I mentioned already, about 1 gigawatt of power and 8 gigawatt hour of storage capacity. We've been visiting that with some students from Paderborn. Here you see our excursion. It's quite a long journey, so about 5 hours drive one way. And here you see the explanation here. This man is explaining how this plant works. Here you see the grid here. So here the grid is directly connected to the high voltage transmission wires here, to the high voltage transmission. In Germany, the voltage of 380,000 volts. There's also some lower for the city here, a mid voltage with 10 kilovolts to supply energy to the city of Goldistal. Here you see some typical loss diagram of such a diagram for such a power plant. So you have here the electrical input. So first you lose about 0.5% at the transformer. Okay, that's very small, that's negligible. 3% at the motor, about 10% at the pump, 0.5% at the tubing, depending on the size of tubing and the length of the tubes and so on. Then you have here the storage lake. And then you release it from the storage lake. You have again some tubing losses. Depends on the velocity, as I mentioned, and on the diameter of the tubes and length of the tubes. Then about 8% at the turbine. So you see it's a bit higher than the pump loss, a bit lower than the pump losses. Then about 2% at the generator. Again, 0.5% at the transformer. So they are remaining 77% as electrical energy output. If you take a look at other neighboring countries, there's also potential in Austria and Switzerland, but by far the largest potential is in Norway. There is a potential of some interconnected lakes in the vicinity of 7.8 terawatt hours. They're not gigawatt hours like Goldistal, but terawatt hour. This is 1,000 times more than Goldistal. So if there would be a good connection to that lake system, we would have power for about a week in Germany, or a bit less than a week, 5 to 7 days. And this would be sufficient to supply energy even during times of low irradiance and low wind velocities. There is already a connection set up. It's not in operation yet. It should come into operation within the next couple of months, but the maximum power to be transmitted through that connection is about 1.4 gigawatt. Could be really much more, just in the vicinity of 10 times more, 20 times more, would be very helpful to go on with German Energiewende. Here just an overview, if you take a look at the data sheet of pumped storage hydropower plants, you have an efficiency of 65 to 85%, power from 2.3 megawatts to about 1 gigawatt in Germany, to say, and storage capacity in Germany is 8 gigawatt hours. And if you go to other countries, if you see Norway, it could be even 1,000 times more. Energy density is 0.35 to 1.12 kilowatt hours per cubic meter. discharge time 5 to 10 hours, depending on the demand. If you have a really large reservoir, why not using it for weeks or even months and use it as a seasonal storage. Self-discharge rate, depending on the temperature, is 0 to 0.5% per day. The cycle numbers is almost unlimited, depends on how long your civil engineering construction lasts. So usually these kind of plants are planned for operation times of 100 years. The specific investments costs are 100 to 500 euro per kilowatt hour of storage capacity. It's marketable. It's the oldest of such power plants are in operation for almost 100 years. And new develop underground pumped storage is a new potential to do that, to reduce the environmental impacts. Even you can use this almost century-old factory for modernization. Problem in Germany are the limited locations, but as I mentioned, there are a lot of neighboring countries which have very favorable locations. Come now to the compressed air storage at CAES. So the principle is you have compressed air and then you release it during, you compress during periods of high availability of electricity, and you release it through air turbine during periods of low availability. As storage, it's too expensive to make artificial storage from of steel tanks or so on. What you use is already existing caverns, depleted wells or aquifers. The compressed air can be released and run through turbines to generate power if wind turbines and solar plants reduce their power output and this power is needed. So already this is the definition of storage need. So here you see that. So you have here our compressor. This is electricity, sure. You have here for low pressure and high pressure. During the compression process, there is a release of heat. If you pump up your bicycle with a air pump, you feel it, it gets hot. And you can use that heat for the preheater, for example. So this means adiabatic use. This improves the efficiency, which is usually quite poor of such CAES system. And here you have the storage, the cavern, use it, and this could be really high and therefore provide power for a long time, even if the air density is relatively low. What is often used here is a combination, hybrid use with natural gas. So you're not only releasing the compressed air, you're also burning natural gas or methane, or it could even be hydrogen. That's not tested yet, but there is a possibility. So it could be even clean hydrogen, and then go through a gas turbine with two stages, high density and low density, to increase the efficiency, and then you have the exhaust outlet and the generator which supplies that electricity to the grid. So it could be used for a wide range of auxiliary services that are similar to those for the pumped hydro storage power plants. So they provide control energy, for example, minute reserves. They smooth the load curve and long-term balancing compensation for windcast errors or solar errors. Usually windcast errors are more serious because if you make an error in wind speed, the output power is affected by the power of 3. And by solar, it's linear. So if you make an error of 10%, you have an error in output power of 10%. For wind, it's much more severe. All these applications serve to secure the stability of the power system. if you're able, for example, to smooth the load curve, then you're able to reduce the maximum power and transmission systems and so on. And this could even lower the operation costs or even avoid necessary investments if you have an increased peak of load. So the CAES, they can react very quickly within a short time, so provision of full power within 8 minutes. So that's a bit less than the 1 minute or 1 to 3 minutes of a hydropower plant, but still much better than most conventional power plants. So they can satisfy a short-term need of energy, they can balance out short-term power fluctuations. The disadvantages, so there are significant heat losses during the compression. Mentioned already some methods to avoid that or to use that energy, and usually the efficiency is in the vicinity of 50%, so here a range of 40 to 54% is given. Large storage volumes required from 300,000 cubic meters to 700,000 cubic meters because the energy density of the storage is relatively small, considering a nominal pressure of 50 to 70 bar. If we compare that, for example, to a car tire, is about 2 bars. A bicycle tires is up to 9 bars for a race bicycle tire. Here our data sheet for our CAES. So application is for peak load control power efficiency 40 to 45%, or sometimes a bit higher. So we saw 54%. The only basically 2 power plants on the world existing. So this is here 110 to 290 megawatt in Germany, in Hundorf. There's another one in McIntosh in the United States. The storage capacity is here 580 megawatt hours. The energy density is 0.5 to 0.8 kilowatt hours per cubic meter, so significantly less than the one of pumped hydro storage power plants. Discharge time 2 to 24 hours. It could be even longer depending on the needs. A self-discharge rate similar to the pumped hydro storage power plants, 0 to 0.5% per day. Also cycle number is theoretically unlimited. Investments costs are 40 to 100 euro per kilowatt hour of storage capacity. Market stage is marketable. Development potential are in the researchers developments, optimization of conversion efficiency, a big issue, and also to make really large devices in the vicinity of a gigawatt. Let's come to the chemical storage, which we start with the hydrogen storage. So the principle is we apply a voltage with 2 electrodes into water, and this is called electrolysis because we generate oxygen and hydrogen. The storage of gases or liquid hydrogen is similar to the natural gas storage, so in pressure vessels and possibility future underground salt caverns. Our economical minister is very much in favor of that technology, so he's just really keen on having a kind of hydrogen economy. So during periods of an energy surplus, for example at wind power, stormy periods, or in summer with photovoltaics, and usually there's a holiday period and people are not are away on holidays, and demand is low but generation is high, and so you want to store that surplus in energy. And you can convert that electrical energy into hydrogen via electrolysis and then store. During peak time of consumption, when the actual grid power is insufficient, the stored hydrogen will be converted back into electricity. This chemical reaction of the electrolysis is here water is transformed, 2 hydrogen molecules are transformed in 2 hydrogen molecules and 1 oxygen molecule. So this is a system design here, a schematic here. So you have here, for example, wind. You either feed it into electricity network when electricity is needed. If it's not needed, you use electrolyzer and convert water into hydrogen and oxygen. Usually you don't store the oxygen because it's available from the air, and additionally oxygen is quite aggressive, and so the storage tank would be relatively expensive. So you just use a hydrogen, and you can put it into the hydrogen network, which is really small actually in Germany, but according to our minister, he says he wants to extend it significantly. Additionally, there's a possibility to add some hydrogen to the existing methane infrastructure, the so-called Stadtgas, city gas, formerly has been consisting of 50% of hydrogen in former times. So this shouldn't be a big problem if you use at least small amounts of hydrogen into the methane infrastructure. Here you see the conversion of that hydrogen via fuel cell back into electricity. You can also use a turbine, but usually hydrogen turbine efficiency is not so well, it's in the vicinity of 50%, while fuel cell conversion efficiency is a bit higher, but usually much more expensive. So we see here a small movie. I hope it will work.
Welcome to the group exhibit Hydrogen Fuel Cells and Batteries at the Hanover Fair 2017. My name is Muriel Burkas and we're here at the Technical Forum. We're here for the last presentation of today and I'm very much looking forward. It will be about PEM electrolyzers improving transformation costs through intelligent stack design. Please welcome on stage with me Head of R&D of HTech Systems, Dr. Frank Alibrod.
Thank you very much for the kind introduction. As mentioned, my name is Frank Alibrod. I work for HTech since more than 2 years now. And I would start by giving you a short introduction into the company HTech. HTech is a pretty old company in the field. It was founded in around 1997. And it was involved in some very nice and very challenging products and projects around the field of hydrogen, but now we focused on PEM electrolysis. In 2010, GP Joule integrated HTEC Systems as a subsidiary within the company. We have now 2 offices in Germany. One is located in Lübeck in the north of Germany. The other is located in the south, close to Augsburg in Bavaria. We have one goal at HTEC, and our goal is the most inexpensive conversion of electricity into hydrogen using PEM electrolysis. Our mother company is GP Joule, which is a pretty young company compared to HTEC. It was founded in 2009, but has already 190 employees. GP Joule is a player around the field of renewable energy, with the goal to supply renewable energy round the clock 100%. We have offices in Reusen-Köbel, the head office, very north, in Lübeck, Berlin, Buttenwiesen, and Geislingen an der Steige in the south of Germany, and also international offices in Toronto and in Los Gatos in the United States. So hydrogen is now. This is our new slogan. We often talk that hydrogen is the future, but we think, or we know, it's already the present. It is pretty easy to put hydrogen, if it's produced from renewable energies, directly into the gas grid. That's one opportunity. You can do methanization and use the methane for different purposes. Of course, mobility. We all know the Mirides, the fuel cell cars. You can use it for fuel cells. Of course, there's industrial applications, chemical applications, and what's the future? It's the reconversion into electricity. So the PEM electrolysis cost breakdown. There's one study saying what actually are the cost breaks, the costs for a PEM system and for a PEM stack. On the left-hand side, we see that a stack contributes more than half to a PEM electrolysis system. On the other side, we see the cost breakdown of a PEM electrolysis stack, saying here that we have 51% only for the bipolar plates. That's a European study, the final report, which was announced just a few years ago. Actually, I must be honest, this is not our costs. I'm actually not allowed to give you the costs, but let's say it's not so far away from the truth that we see it. But when we have such a cost breakdown, we can think about what will we do to reduce those costs. Of course, first we ask us what are the most expensive components. If we have identified them, we can of course say, let's reduce the costs on them. Can they be replaced? Do we really need them? Or can we reduce the waste, which is actually a very nice possibility to reduce cost. We talk to all our suppliers, and then we say, okay, what's the best compromise that every supplier has the fewest waste, and by that we can decrease the costs for the entire stack. And of course, there's another possibility to reduce costs is by mass production, thinking from the beginning. Not only think, what's the cheapest way to produce it in 10 or hundreds. Just think from the beginning. Let's produce 10,000. Let's produce 100,000. That's what we need for the future energy system. And of course, if it comes to 10,000 and 100,000, there must be also the possibility to manufacture it by robots. Think about limitations by the suppliers. Can they, if you have a good supplier, but can the supplier also distribute 10 times, 100 times more as he is distributing now? And of course, one challenging point, especially if it comes to PEM electrolysis, is the availability of raw materials. Do we have enough iridium, platinum on the planet? Can it be produced? Can it be mined? And of course, there's also another possibility just by using the overload capability of the stack. So it's pretty easy to have a stack and put 400% on it, then you have very low specific cost, but the lifetime is a disaster. So you have to find an intermediate way. So we did this, and the first result is what we are very proud of, that we are now able to sell a PEM electrolysis stack, the so-called HTEC S-series, with a weighted production of 0.40 to 3.38 kilograms of hydrogen per day. If you want to just have a S30/10, it comes with 1 kilowatt electric power. It's pretty easy to calculate. Each cell of those stacks has 100 watts. The load range is in between 0.2 to 6 kilowatt until 9.4 kilowatts. We have an overload capability of 188%. We are also able to give a mean MTTF, mean time to failure, and we say this is 40,000 hours now. We've done some very intensive testing in the last years with a total testing time of over 100,000 hours. And with our newest design, we didn't have any failure. As well, we didn't see any significant degradation. It was almost zero. Also, what is pretty new this year is our M-series electrolyzer. So we stepped back. We don't sell only stacks. We also sell electrolyzers. This is the ME100/350, and it produces 100 kilogram of hydrogen each day. The maximum power is 350 kilowatts. And in overload, we can also produce 140 kilograms of hydrogen per day. So, and there's one more thing what we offer with this electrolyzers. This is a guarantee of 4 years. So it's called our performance guarantee, and it comes together with a maintenance contract. So if you want to hear any more details about purchasing such an electrolyzer or purchasing a PEM electrolysis stack, our booth is pretty close, C58, and we can give you pricing and everything on the booth. So the data sheets are available as well for both products that we offer, and I would be very happy to introduce you more detailed into our products at our booth. Thank you very much for listening.
Thank you very much for your time and your spontaneous presentation. Are there any questions for him? No? Okay, I think call it a day at the technical forum. As he announced, if you have further questions, go to the booth later on or tomorrow or this week. I hope you enjoyed the technical forum on the first day, and we will start tomorrow at 10 a.m. with the first presentations right here. Okay. Have a good afternoon, evening, and see you tomorrow. Thank you very much.
Okay.
This was about the reconversion via fuel cell. We just talk about more general observation now of hydrogen storage. So we see the advantages and disadvantages, but let's first start with some general characteristics. So the first application of hydrogen storage has been the balancing of power deficits of surpluses as a result of forecast errors of wind and solar PV. While it can be supplied within a relatively short period of time, prices can be elevated. So this is could be quite profitable, but still, the moment the prices of the electrolysis and reconversion is much higher than the price you can get on the electricity market. Hydrogen storage can serve a long-term storage, thus providing electricity during days and wind and solar irradiance. Hydrogen storage can store a large amount of energy surplus during high wind periods, whereas that energy could be lost if the wind turbines would be throttled. The advantages and disadvantages are substantial. Advantages is its normal storage capacity, because not the tanks are so big, but the energy density is quite high. The energy density it could be reconverted, as we saw, via fuel cells or via conventional gas steam power plants. This energy density is 163 kilowatt hours per cubic meter. If you compare it to pumped hydro storage power plant, it's only about 1 kilowatt hour per cubic meter. This big disadvantage is that the relatively low conversion efficiency. So due to the compression, you lose additional power, plus the electrolysis, plus the fuel cell reconversion, or even worse, reconversion via turbines. So you have about 40% of conversion efficiencies. Come to this later. There are some efforts to improve that conversion efficiency, even if you consider methane, not hydrogen. But I will tell you in about 5 minutes. If fuel cells are considered as for reconversion, the planner should be aware that the major part of fuel cells are prototypes only. As we saw, this was a video from the Hanover Fair. There are some smaller startups which want to go away from the prototype status and want to go into mass manufacturing. Here, just our data sheet. So we have here application, peak load or control power, or even in future seasonal long-term storage. Efficiency in the vicinity 40%. We see that it's getting better here. Power and the kilowatt to the gigawatt range. Theoretical storage capacity, we come to this a bit later, is about 1,300 gigawatt hours. Energy density 333 kilowatt hours per kilogram, not per cubic meter, but per kilogram. The other one has been 136 per cubic meter, compressed already. And discharge time is seconds to days. Self-discharge rate, there's no significant self-discharge. Actually, the infrastructure has to be very tight because the molecules, hydrogen molecule is very small. And so you have really to have very small, good tightening valves and pipelines into tanks and so on. Specific investment cost is a big discussion. So how much does it cost? Because it's from the stage, from the prototypes to mass production, but still it's hard to find really a good price development. Power to gas, that's heavily under discussion at the moment. So you're just not only doing hydrogen, but convert that hydrogen into methane. So here, this electrolysis, here an example of the PEM cell with a conversion efficiency of 73%. And then you can redox reaction. So you have here the electrolysis from water into hydrogen and oxygen. The idea is now with the addition of carbon dioxide to form natural gas or methane. So you do the so-called methanization or methanation from both in the literature. So you convert carbon monoxide or in particular carbon dioxide into methane. So you have here the atmosphere, the biogas plant, and you have here the conversion of, get this from the atmosphere, but the concentration actually of carbon dioxide is relatively small. We have this number in the atmosphere, we have about 415 parts per million. So less than 0.5% of the atmosphere is carbon dioxide. So it's much easier probably to get this carbon dioxide from a biomass plant and then converted from the hydrogen which you created from electrolytes into CH4, and that's exactly methane. Efficiency can be up to 80%. With the European project Helmet, I'll show you the website a bit later. And the reaction is here for hydrogen molecules are reacting with carbon dioxide to methane and some water, to water molecules. Fortunately, I didn't get this graph in German, but I quickly explain you the these so-called Sankey diagrams, or kind of loss diagram. So that's the first is a power to gas. So you have electrical energy and convert it into hydrogen. You see the losses here at the transformer are not very big, or most of the losses are here in the electrolysis part here. This is the losses here, the blue part. You see the loss of 23.7%. Also compression, there are some losses, but not so big as I expected. And then there is transportation. Here is taking a transport of 500 kilometers. And at the end, you have about 70% of total efficiency from power to gas. If you use power to gas in the form of methane, then efficiency is a bit lower, because you still have to do the methanization or methanation here, and there you have an additional loss of 14.2%. Then you have still the same for transportation and so on. So altogether, you have an overall efficiency from power to gas or power to methane of 56%. The sectors of use where you can use hydrogen, so you can use hydrogen as a raw material for industry, particularly the steel industry needs hydrogen. You can use it for mobility, because the energy content is really high, much higher than in batteries, and you can use it as a fuel. Even some of the spaceships are powered by hydrogen due to its high energy density. And you can use it for cars, lorries, buses, or even trains, or airplanes even. Heat supply, sure, you can use it as a conventional heating fuel and heat a room, or as I mentioned already, for electricity generation, and go via fuel cell or turbine. So here you have the turbine efficiency. So conventional gas turbine has a vicinity efficiency in the vicinity of 40%. If you use combined cycle power plants, you end up at 60% of total conversion efficiency. Peak load capability, start times about 10 minutes, even more modern one. Got a new data sheet from the Kawasaki company, which is able to start up within 5 minutes. So on, and that's relatively fast compared to coal power plants and nuclear power plants, which sometimes even can take minutes or hours to follow the load. This is a project I mentioned here, this helmet. This combines methanation and electrolysis with a total efficiency of 76%, so much more than the 56% I've been showing you before. Want to give you some details. Here you find the website, helmet.eu is the website of the project. There are even more details given then. The basic idea is to make optimal use of the process heat for methanization to cover the heat consumption of the electrolysis. So do a high pressure, a high temperature electrolysis in the vicinity of about 800 degrees Celsius, and therefore you can increase the efficiency. Yes, this power is used to decompose water into oxygen and hydrogen. And then this hydrogen reacts with carbon dioxide or even carbon monoxide to methane, and then you have this natural gas, and the heat is released. Yes, the advantage of why use methane, it's basically the existing infrastructure you have. There are a lot of pipelines, tankers, terminals, and even cars which can directly run with methanes. If you have a conventional diesel or auto engine, the conversion into a natural gas or methane engine is not very big. Even for the turbines, a lot of methane turbines, but only a very few manufacturer of hydrogen turbines or hydrogen engines and so on. Another movie here. hope I can start it here. I shall give you an overview about the potential and costs of this power to gas, especially in particular power to methane technology. So in Germany, we have an actual electricity consumption of 600 terawatt hours electrical, and about the maximum power to be needed is about 70 gigawatt. The storage capacity, the existing one and potential one, just at the moment we have a pumped hydro storage battery and so on in the vicinity of 0.07 terawatt hours, so this would last only a couple of minutes. As I mentioned before, just we have a consumption per day in the vicinity of 1.5 terawatt hours. With the e-mobility, so this could be more interesting. So if we consider 45 million electrical vehicles, and then we would have a capacity of 0.45 terawatt hours, and this would give a range of about 6 hours of German electricity consumption. And gas power, that capacity, due to the large infrastructure, this would provide 130 terawatt hours of electrical power. This would range to 2 months. So, for example, we can use only photovoltaic power supply, and during the harshest winter months, December and January, we would supply all via the stored gas power. The costs are in the vicinity of 1,000 to 1,500 euro per kilowatt. So this contains the compressor, electrolysis, methanization, about this. This leads to energy supply costs, considering also the lifetime of that systems, so of 2 to 3 cents per kilowatt hour of thermal energy, and about 8 cents for electrical energy from reconversion of methane, and that's still expensive. So if we compare it to the cheapest tenders and photovoltaics in Germany, have been in the vicinity of 4 cents per kilowatt hour electrical one. So this is still quite expensive, and it cannot compete against fossil methane. So advantages, okay, like every storage, electricity from renewables is available around the clock. Wind turbines and PV systems must not switch off, so you can use the surplus to generate hydrogen or methane. Yes, sure, you have a reduction of CO2 emissions, grid stabilization. Disadvantages are, yes, investment costs are higher, and there's some constant development, but still it's a bit away from the actual competitiveness against fossil methane. Efficiency, as you saw, this Helmut project provides an efficiency in the vicinity of 80%, at least for the process from electricity towards methane. For the reconversion, okay, you have to consider that also. Then overall efficiency is vicinity of 50% and so on. Let's come to traditional storage, small-scale storage, the lead-acid battery. So this lead-acid battery is quite old. So it has been invented in 1859 by the French physicist Gaston Planté, and this is still quite often used still today. Till a decade ago, this was the most often used chemical storage. Nowadays, lithium-ion batteries got much cheaper, and so most of the companies which produce the lead-acid batteries are switching to lithium-ion technologies. But let's discuss, because they're still often used, for example, in car batteries and so on. So these batteries are relatively cheap, and they can supply high surge currents. Each cell can provide a nominal voltage of 2 volts that can be increased via the series connection of battery cells. Such a typical car battery with a lead-acid battery consists of 6 cells, so you have a nominal voltage of 12 volts. The principle is you have 2 electrode plates, one consisting of pure lead and the other one of lead oxide surface, and they are in an electrolyte that consists of thin sulfuric acid. Typically you have an acid content of 37%. During discharging, both electrodes turn into lead sulfate, PbSO4, and the electrolyte turns into water, and therefore this is just a reminder, it's not so important here, but lead-acid batteries, they can freeze if they are discharged, because then you have more water in the battery rather than this thin sulfuric acid. Here you see the formula here. If you look at discharging, it goes this direction. So we have here from the positive electrode PbO2, negative electrode lead, and then you have here the sulfuric acid here, and this turns into lead sulfate and water. You can also measure the state of the battery by measuring the weight of the electrolyte, the density of the electrolyte. So because the sulfuric acid is much heavier than water, and if you have a density of 1 kilogram per liter, its battery is completely discharged. If you have in the vicinity of 1.3 kilogram per liter, then the battery has this about the maximum of sulfuric acid. At charging goes vice versa. So the lead sulfate of both electrodes is converted back into a lead oxide at the positive electrode, or lead, or exactly sponge lead at the negative electrode. And the sulfide ions are driven back into the electrolyte. Application, as I mentioned already, these are typical automotive batteries. They are often called SLA, starting lightning ignition batteries. So they do not suffer deep discharge, so they are just used for some seconds to start an engine or to use a light in case the motor and its connected generator don't work, also for ignition and so on. It's designed as for short time, high power output, and not for deep cycling. Often this type is still used for a solar application because it's easily available and relatively inexpensive, but lifetime is relatively short because this kind of batteries are not designed for that. In order to increase a little bit the lifetime, the depth of discharge DOD should not be higher than 50%. That's just a hint to avoid acid stratification and sulfatation, which limits the lifetime. The battery should sometimes be charged at gassing potential for a short time. That creates bubbles from electrolysis and therefore avoids the stratification. So some charge controllers have this option already included, so they do it for 2 to 5 minutes twice a week. Mechanical shaking may not help because the spacing between the plates is usually too small to ensure the mixing. Industrial batteries, they are for traction or stationary application, for cyclic application, and also they can support the discharge. Therefore, they use thicker plates and tubular electrodes. The active mass in the tubular electrodes is armed with a plastic protector in order to avoid mass shedding. So some of the sulfate may not fall off. And the tubular type is often used also for solar application. Yes, it's still low, this specific kilowatt hours costs. Solar batteries, they have some improved behavior, as mentioned before, thicker plates and so on. Yes, you can improve car batteries usually made. That's the manufacturer of car batteries. They produce in the same size and the same, almost same specification, solar batteries. It's just using thicker electrodes. They enclose the electrodes in special pockets, separators, and they use excess electrolyte. So they make them bigger or rate them at a lower capacity, and they use grids made from low antimony or antimony-free alloys to reduce gassing and self-discharge. Okay, let's come to the properties. So you see here the impact of the operating temperature. So you see here at the impact of the operating temperature for the self-discharge. So you see clearly the higher the temperature, the much higher is the self-discharge. For example, if you have some tropical location where you have 40 degrees ambient temperature, the battery is self-discharged by 50% within 6 months. If you have it at 20 degrees, it's almost 18 months possible. Additionally, the lifetime is very much reduced at high temperature, but we come to this a bit later. Here you see the lifetime as a function of depth of discharge, DOD. So here you see this consumer battery, and if you discharge at a very high rate, then lifetime is very, very short. So you can do only a couple of cycles. If you come to 50%, it's still very short. So it's here in the vicinity of 300, 400. So that means you have a lifetime, depending on how much cycles where you do a daily cycle. But if you do a daily cycle, it's also lifetime is limited to 1 year. If you would do the same for industrial batteries, the lifetime in cycles would be 2,000 years. If we reduce it a bit here to the depth of discharge to, for example, 35%, then lifetime is 3,000 cycle. That means it's about equivalent to 10 years of lifetime if you do a daily cycling. This I mentioned already, the temperature impact. So this lead-acid battery is the red line, and mentioned, so if you have at laboratory conditions or mid-European conditions 20 degrees of operation temperature, and you would apply the same battery to a tropical location with ambient temperature, operation temperature of 30 degrees, lifetime is really reduced to half of it. So that's quite unexpected. So you see that just this 10 degrees in increase leads to a 40 to 50% reduction in lifetime. This is an advantage, we come to that later, of a nickel-cadmium battery. This is also for the lithium-ion batteries. It's less sensible to temperature changes. Here you see the capacity as a function of discharge current. So you see here, if you have a relatively low discharge current, you can use about 100% of the usable capacity at 25 degrees. If temperature is low, it goes down near 80% or sometimes 70%. That's typically in winter when the car batteries. Problem is if you have high discharge current, this is usually the case if you have a car in winter and you want to start it, the viscosity of the motor oil is very low, and so you need a really high current, and then the available capacity is going down here, for example, to 50%. This is related to a 12 volt 100 ampere hours battery, so this is already 20 amps for this battery is quite high, but if you think about starting a car, you easily can go up to 100 ampere of current, necessary current to turn the ignition. VRLR batteries, maintenance-free batteries, usually when batteries are overcharged, they produce hydrogen, and there's a consequential loss of water. You have to refill that water with distilled water. Sometimes it's a problem to get distilled water. and you have to have some reliable person who is doing that in a regular way. And sealed units, they minimize that loss, so the hydrogen, the oxygen cannot escape. Then sometimes you have some catalysts who allow a regeneration, and therefore it's called maintenance-free. But a well-maintained open batteries has a longer lifetime than a VLR battery. This has been to reduce the effect, so the oxygen being developed at the positive electrode is transported to a negative electrode and then reduced back to the water via a catalysator. The cost of the batteries as a function of capacity, you see here, so small batteries are very small batteries are quite expensive, so mid-size are the cheapest one here, so in the vicinity of about 100 euro per kilowatt hour. When you come to industrial battery, they usually are not so often sold as, for example, car batteries, and they are a bit expensive. Only if you go to a very large size, you have here some price reduction. Nickel-cadmium batteries, they have some advantages over lead-acid batteries. So they have a higher energy density than lead-acid batteries. They can be fully discharged, so lifetime is not suffering so much from discharge. So they don't need to be oversized. They are more rugged, and they have much better temperature performance. They have a lower internal resistance that permit high currents, and they can also more quickly charged and discharged within 30 minutes. And also they maintain a relatively uniform voltage during discharge, and they have low maintenance requirements. They have also some disadvantages. So they are typically 2 times more expensive. They have lower energy efficiencies. While you have 80 to 90% at lead-acid batteries, here at nickel-cadmium batteries, it's only 75%. Yes, you have this memory effect. So contrary to the lead-acid batteries, which you shouldn't cycle so much, they need sometimes cycling to avoid the so-called memory effect. So if you only cycle about 10% of the possible discharge, the battery thinks that it has a reduced capacity and it's not able to discharge any deeper. And this is called memory effect. And therefore they have to discharge once in a while to zero. Cadmium is a hazardous material, so it is important to make sure that the battery is not disposed but recycled after usable lifetime, but the same applies to lead also. Let's come to the most modern battery, the lithium-ion battery. How does a lithium-ion battery work? So we start with the history of the lithium-ion battery. We spend a bit more time for the lithium-ion batteries because probably it will be the only chemical battery that will survive. Or there will be a complete other technologies, but I don't think so at the moment. And the second chapter is here, the lithium-ion battery as a rechargeable batteries. First, it was a primary cell. This is non-rechargeable. Then I will discuss a little bit about the process of charging and the discharging. How does a lithium-ion cell work? The range of materials for electrodes and operation properties, the share of costs. So how can we possibly make a lithium-ion battery cheaper? What's most expensive? Is it material, or is it processing costs, or labor costs, or energy costs, and so on? Discussed here, and the perspectives. Let's first go into history. Lithium-ion battery as a primary cell, so as a non-rechargeable battery, is quite old. So it's been used since the 60s for space and military applications. In the 70s, it's also been used in computer technology for permanent storage, for internal clocks of computers. and since the 80s they are used for consumer application. So bottom cells, or you can even buy them in supermarkets. So micro and mignon cells or 9-volt blocks. They are usually more expensive, but our lifetime is much longer. So for example, if you have fire alarm monitors, usually they have lithium 9-volt blocks. Advantages, they offer a single cell high voltages up to 4 volts compared to 1.2 to 1.5 volt at conventional battery systems. They have a high specific power and energy density of 300 to 400 watt hours per kilogram. They have hard characteristic of discharge. That means that the voltage stays constant for a wide operation point. It means also at a high discharge level, or if the battery is almost empty, you still have the full voltage. You have a wide temperature range of operation, so specifically at low temperatures, and you have a low self-discharge rate, so you can have a storage possibility of about almost 10 years. Come now to rechargeable battery or secondary battery. This history is much younger. So in the 1980, Professor Goodenough from the University of Oxford has proven lithium cobalt dioxide is a suitable electrode material, and he together with Mr. Mantiraman from the University of Texas, he showed that the electrodes that contain sulfates, they provide a higher voltage than the formerly used oxides. Interestingly, in the same year, there was a patent by the German Peter Busch on a lithium-ion accumulator, including he presented a prototypes, but there was no interest by investors in industry. Independently from that, Sony and Asahi and Kasai, they just manufactured their own lithium-ion accumulator without considering that patent. In 2002, there was another step in lithium-ion history because the electrolytes, the liquid electrolytes, have been substituted by polymer foils, and so you don't need any containment anymore against liquids. So you just have to use a foil pile, and so it's much more easier to fabricate, and also you have a lower weight. Let's take a look at the functioning of a lithium-ion battery. So first we take a look at the discharge condition. So we have two electrodes. While it's discharged, we don't have any positive or negative. It's completely discharged, even short circuits. And so you have here copper electrode, and there's a lattice of a carbon, a graphene here, a C6. And on the other side, you have lithium cobalt dioxide here. So the lithium atoms are the smallest. Then you have the oxide, dioxide, which are relatively small, and the cobalt atoms. Could be not, it's not necessary cobalt. You can also use manganese, nickel, or even iron. We come to this a bit later. So now we start charging the battery. So we supply electrons here to the copper electrode here, and we take away electrodes here from the aluminium electrodes, and we take specifically we take the electron away from the lithium atoms. So we have here lithium ions here positively charged because we took away this the electron, and get them here. So there's negative charge here. So they try to go to the other electrodes. We have a separator in between. It acts as a filter. So the size of the holes in the separator have exactly the size that the lithium ions can pass, and the rest not. And if we continue charging, so this is a chemical formula for that. So we have cobalt dioxide and lithium ions and electrodes here, and you can do it also multiple times, therefore it's in X here. So it's not necessary that you just only do one ion and so on, you can do multiple of those. And on the other side, you receive an electron here, and this combines with the lithium ion to lithium, and it's stored in the carbon lattice. Just to mention, you can also use other materials, as I mentioned, also manganese and so on. So the formula looks a bit different, but not very, but the principle is the same. Here we have now the condition of 100% charged lithium-ion battery. So there's almost no lithium anymore on the anode, all on the cathode here, and we have here the stored lithium. The lithium atoms now don't anymore ions, so they are in this carbon lattice. So we start to discharge now. So we have here a supply of electrons here, and they go in that direction. If you take away electron from the lithium atom, it turns into ion, and this ion is transported here because there's a negative charge here through the separator to the anode. This is our load here, and this is our current source. I know that is a current, not the current source, it's just ampere meter. So just ampere meter load, and just we discharge. If we charge, we need a source, but here we don't need a source. So here again the formula. So we have here the LeC6 turns into lithium ions plus the old lattice of carbon plus an electron. And here we get an electron, could be also multiple, as I mentioned already, and turn back into the original condition that is set. So how are the lithium ions stored in the carbon grid or carbon lattice? So it's called intercalation. It's a bit different from a pure chemical reaction. It's a bit less than a chemical reaction. Why it's not a chemical reaction? Because it doesn't significantly alter the structure during the process of incorporation and removal. So this structure looks still the same before and after the charge or discharging process. So they are just embedded in the carbon lattices and redeposit later. You see, go in and out, and they don't change anything. So it's almost like a conventional electrical capacitor. Here you have this, the art here is at these lattice, so there's graphene layers and so on, and you have to design them adequately so they are able to store these lithium atoms. What is a separator for? It serves for the mechanical and electrical separation of the electrodes. So it's a kind of filter which lets a lithium ion pass, but not the electrolyte. You see that, so the other atoms cannot pass, just only the lithium ions. Usually designed by polyethylene or polypropylene foil, which is initially has a thickness of 15 to 25 micrometers. Then you stretch it during heating up, and then you create some holes, so you create some porosity, and if it's done in a very defined way, you can create exactly holes in the size you need. Also, it serves against short circuits, the growth of so-called dendrites. So these are like dripstones by the accumulation, by the inhomogeneous accumulation of lithium atoms, which may happen if you have a very high current, or if the manufacturing of the battery is not done in a very homogeneous way. And sure, if you have a dripstone that leads to the other electrode, it creates a short circuit, and it can even lead to explosion of the battery. So you want to avoid it. Therefore, the separator is quite essential. In short words, the cell reaction of a lithium-ion battery is based on a very reversible lithium-ion storage reaction. The electrolyte is an inactive material, so can be mentioned minimum in size. The thin electrodes that are piled and wrapped together with relatively high voltage levels allow high energy density. Energy density is described here. Just one parameter is the voltage, and here you see the difference here between the electrodes, the voltage difference. So usually you use here these materials in blue and the one in reds, and so you are sure that you have a high voltage difference and therefore a high energy density. Here are some examples here from materials. We discussed the first one, lithium cobalt dioxide has a difference in electrical potential of 3.7 volts, and it has a theoretical energy density of 518 watt-hours per kilogram. Accordingly, you have for the negative electrode this graphite LiC6, what we discussed here. Okay, there's neglectable difference in electrical potential. Also, specific energy is quite low, but you can think about different materials in order to increase it. But these are own prototypes only, and also if you think about germanium, this is rather expensive and not available everywhere. So this is also, some of these manganese, this is often used. So this is a higher voltage but lower specific energy and so on. To come to here, this looks quite promising, nickel-nitrium oxide, and so lower voltage, but here a higher energy density. Depends on the different parameters, and so I don't want to go into details. Here some access about future development of lithium-ion batteries. So you see here that's still the present, this is from 2010 here, but still this didn't change a lot. This is from the Berger Consulting in 2010. I don't know why it's not visible here to see that copyright here, and here you have here the different developments, and so in the future 2020 is expect to have higher specific energy densities and so on. The light blue one is for the battery pack, and the dark blue one is for the single cells here. Here's also during this study there was also made a cost share. Usually these information is quite secret, so I couldn't even find any new one, but still it gives you a hint how the costs are divided. So you have here the cost of the raw material. This in total costs about $500 per kilowatt hour of storage, battery storage. Nowadays it's 150, even rumors are saying that $100 per kilowatt hour already reached. So this was a decade ago, so this was quite expensive. Maybe the distribution is still the same, so there's 17% of raw materials, 22% of the material processing, and here you see the material cost split. So most is for the cathode, 13% for the anode, and about 14% for the separator, for the electrolyte 9%, and for the other material, copper foil, aluminium foil for the electrode material, binder and hardware. See depreciation, that means that the machines you used for manufacturing are getting old and you have to invest new ones, and this is called depreciation. Direct labor, energy doesn't take so much, overhead. So margin, this is a profit here of the, this is a development of the battery. So this is a cost development here. by Bloomberg in 2019. So you see here in 2013, the cost of a pack of batteries still have been in the vicinity of $650 per kilowatt hour. So the cell costed about $446 per kilowatt hour. So this probably was also cell costs. If you saw this former, so this was, yes, it's a cell costs here. If you go 3 years before, it is quite feasible that cell costs are in the vicinity of $500 per kilowatt hour of cell costs, but you have to interconnect them in series and encapsulate them and so on. This is this cost, and together, even in 2013, was $650. And 2 years ago, this cost decreased a lot. So cell costs are only at $127 per kilowatt hour. The pack making is $49, and altogether $176. And this is a German research, and they even estimate that this year we have costs in the vicinity of 108 euro per kilowatt hour. So what is about $120 per kilowatt hour for the whole, not only for the cells, for the whole battery. Quite important is how you treat the batteries. First, significant example is you can discharge theoretically the lithium-ion batteries quite deeply, so they don't suffer such an extent of reduction lifetime as lead-acid batteries, but still you have to consider some issues, and this I will discuss with you in details. This was from a PhD thesis from Mr. CAES from the University here of Aachen, quite new one. And so he shows here, first we will see the so-called calendric aging. So you don't do nothing, you keep the battery stored, and you see how long, what's the available relative capacity after the storage. There was a quite interesting result. If you store the battery fully charged, it happens sometimes because people are used to do that from the lead-acid battery, so they always keep the battery fully charged, or the notebooks are always connected to the electricity supply, or so do the cell phones. And you see that's not very favorable. So just by this storage, you reduce significant amount of relative capacity by that. So much more recommendable if you keep them stored at a relatively low state of charge, SOC. So that's more recommendable if you keep them charged. It's not so recommendable to discharge them totally, but some amount is quite recommendable here. This is very different to the lead-acid batteries. This is now the degradation of lithium-ion batteries as a function of temperature. So you see here at all batteries, so lifetime is longer. So this is a number of days, but this is proportional to the numbers of full storage cycles. You see here, if you keep the battery cool, lifetime is really, really long. If the battery is warm here for 60 degrees, lifetime is really shortened. Also, if you charge your battery, for example, your cell phone very quickly, you feel that it's getting warm, and that's not recommendable because it will reduce the lifetime. If you charge it in a more slower way and temperature stays lower, then a lifetime is much higher. Here now is something interesting. So you the way of cycling. So this is delta SOC. That means here, for example, the blue curve, that you mean you always use a full capacity. You always do a full cycle. So you charge the battery fully and discharge them completely. Average between 0 and 100 is 50. And then you see this blue line. Lifetime is really short. So this is not so recommendable. If you charge your battery more often, for example, if you just use 20% of the capacity, so you, for example, medium is here 50%, that means you charge them to 60% and discharge them to 40%. So you have a delta SOC of 20%. And if you follow that curve, you see that you have a lifetime which is about 3 times as long here. So this also, if you treat your cell phone battery, not always fully charge them, this can do also, it's quite a good idea. This is not so recommend. So it's always good to keep them in a medium level, charged and discharged. And here, this is as a reference. If you don't use a battery at all, this is not realistic. But here you see that best if you have only 5% of charge and discharge. Here, you see here. So you have here the depth of discharge only 5%. That means here from 50, while the medium is 50%. So from 50. Wait a minute. This is. No, wait a minute, this is the other curve here. Yeah, so you just cycle it from 52.5% to 47.5%. Here the cyclical aging, so the importance of the SOC level. So as I mentioned, if you keep it medium here, you have the best lifetime. So you always keep the battery operating in the medium charge state of charge here. This would be the red line. If you either fully discharge them or keep it at a very low charge level, lifetime is very short. So you see this blue curve. This is very, very, very low state of charge, and this light green line is a very, very high state of charge. So recommendable is this line, and that means we always keep the battery medium charged. Last but not least, we come to the electrical storage, the so-called double layer capacitors or ultra capacitors. These consist of electrodes that are surrounded by electrode. If a voltage is applied, ions accumulate at both electrodes of inverse polarity, like a conventional electrical capacitor works. The energy is stored in the form of the electrical field on the electrodes and the ions of the electrolyte in between the carriers. The electrode with the dielectric behave as two capacitors connected in series over the electrolyte. So you see here this one. So you have here this is the electrolyte. This is the fixed electrode here, and this acts as a capacitor because here we have the negative, the electrons, and here we have positive charges, and here's vice versa. So this is actually like two capacitors interconnected in series here. Here also you have a separator similar to the separator at the lithium-ion battery. Again, here you see the temperature influence. So here life in months, here you have a very long time of this battery, and if temperature goes up, lifetime is very much reduced. And so is the applied voltage for the supercapacitor, because they may destroy the electrolyte. So they are very sensible against overvoltage. So best keep them at this here 2.3 volts rather instead of 2.5 volts. You are sure you have a higher energy density, but the lifetime is very significantly reduced. Here is a data sheet of a typical ultra capacitor by the company Maxwell in 2016. This company has been recently brought up by the Tesla company. We see here the rated voltage of that specific capacitor is 2.84 volts. This is a really high capacity, typically 3.4 kilofarad or 3,400 farad. This was some decades ago was really impossible. So the 1 farad was really high value, and most of the purchasable capacitors, they have the best ones, electrolyte capacitors, they have vicinity of 600 microfarads, or and this is that you have farads or even kilofarads is was thought as an impossible thing. This is the internal resistance, so this determines how fast you can discharge them and how big the heating up is. If you have really high discharge rates and If you have a high resistance there, then you have considerable heating there, and this may destroy the capacitor. So if you have just a 0.28, so it's really low, so you can really supply a high discharge current. Here you have a specific current, so 6.7 kilowatt per kilogram sensor, 8.5 kilowatts. And here there's all this data given, temperature resistance, and so on, what else? Yes, projected lifetime 10 years. This depends really on the, as you saw, on the temperature and on and the voltages you apply then. Absolute maximum current here 2000 amps. That's quite really a lot. So permanent membrane as a separator between the negative and positive electrodes to prevent a short circuit. Storage capacity is determined by the size of the membrane, so the area of the membrane, and the distance between the membranes. So not the same membrane, and the distance between the electrodes. So the thinner you can make the membrane, the higher is the capacity. And the active porous carbon materials are mainly used as materials for the electrode with a large surface. Yes, as I mentioned already, they are often called super caps or ultra caps. And they can store energy very they can store they have a very low access times, so this can be provide energy very quickly, and the range from 0.5 farads to about 5,000 farads. We saw just these a typical device with 3,500 farads. Energy density is quite low, 4 to 5 watt hours, not kilowatt hours, but watt hours per kilogram. Yes, you can vary from cylindrical to rectangular shapes, and the energy stored in a capacitor is given by that, so it's half then as you see. This is the capacitor, the capacity here given in farad, and then the voltage in square, half of it. So they are suitable for applications where loads require a high number of short charge and discharge cycles. For example, you could apply them for acceleration and recuperation in cars or buses and trains, or for stabilizing the voltage in electrical energy systems. They are often used as a battery supporting application, for example, as an emergency power supply for the blades of wind power that have to be turned away from the wind during a failure. Yes, this is mentioned before already, and they also can call it slip control. So this is some applications on that. The decisive advantage is their high power density, not energy density, power density, and thus delivering high amounts of power over a short period of time. Furthermore, the advantages include the high efficiencies, 90 to 95%, high cycle durations and reliability. The disadvantages is that they are very sensitive to overvoltages. You saw this graph here, so if you just increase voltage a little bit more, then lifetime is drastically reduced. Also, if you saw by the formula here that the voltage changes with the state of charge, very contrarily to the conventional chemical batteries, which has a so-called hard characteristic. So even if the battery is almost completely discharged, the voltage almost stays the same. Here not. So if you discharge it, voltage goes down significantly. In comparison to other batteries, they have a very high self-discharge rate, which is in the vicinity of 2.4 to 10% per day. So they are not suitable for long-term energy storage. So the efficiency is quite good, 90 to 95%. Power available in some stacks or some so-called modules of those batteries, from 30 kilowatt to 3 megawatts. Storage capacity is 5 megawatt hours, playing up to 120 megawatt hours. So in general, it's not very impressive, but for this short-term available capacitors, it's quite a lot, because you can have high power delivery. Energy density is relatively low. Discharge time is quite fast, not only 1.5 seconds, you can do 10 times faster. Self-discharge rate is really high, but the number of cycles is really high. Specific investments is quite high. Not sure whether these numbers are correct. This should be even higher than that. And at the very end of the lecture, sorry, this was really a kind of double lecture, so we can skip one lecture, but there was some holidays, but I still want to discuss about the storage technologies in overview. So we will have here the capacity on the x-axis, on the y-axis here the time in hours, the discharge time. And so you see here, for very short time available, you have your double capacitors, what we discussed in the gray color, or you can use a flywheel as a mechanical storage, or conventional batteries. If you want to go to a longer term storage, as we mentioned already, compressed air storage, or here in dark blue, the pumped hydro storage power plants, or here the renewable power methanes. If you want to use the long-term infrastructure, you will have some additional losses, but here you can have a very high storage capacity and also can store it for a very long time. If you use hydrogen only, it's a bit reduced. And here thermal energy storage can also use, but you have to make sure that the conversion efficiency back from thermal energy into electrical energy is quite good. Usually this is quite limited by the temperatures and the Carnot efficiency. Here again, another representation, very similar to the one before, but by another source. This seems to be newer, at least the year 2016 is mentioned here. And here this PTG, power to gas, it's called here synthetic natural gas. It's power to gas technology. Here's just a hydropower, pumped hydro storage, compressed air storage, batteries, and also flywheels, and those capacitors, supercapacitors, which we discussed. This is just under development, superconducting magnetic electrical storage. So I'm not aware of any prototypes or even things on the market. So these are the application here. What you have here, so energy management here for the just with the highest power and discharge time, as you saw before, is pumped hydro or compressed air storage. This power to gas and so on is not mentioned here. Just the conventional types of batteries is in particular the chemical batteries. And if you go to long more supercaps and so on, so you have a very small discharge time, and this serves for a short period of UPS, means uninterruptible power supply. You can use of that, or just short-term power supply and so on. Here, if you have lead-acid batteries, they can work longer. Nowadays, it's a bit older, so you have here, I think it's from 2009, lithium-ion batteries. They are also suitable to have high system power ratings. Here you have the volume density and the weight density here, so kilowatt hours per ton and kilowatt hours per square meter. So this is in particular important for mobile application. So this is from the point of view for the utilities, what you can do that with the different kinds of storage. So here more power, more storage time. So here commodity storage over a long time at high power. This is T and D, means transmission and distribution. Facility deferral. If you have a lot of storage, you can avoid investments in additional transmission lines because you can balance the use of a transmission lines, so there are no peak loads, and so you smooth the load over the transmission line, and so you can avoid some investments cost by that. Here, all the green part is renewable energy management, that as we discussed now. Here's the other applications: power quality and reliability, frequency control, and so on. Yeah, voltage control is also an issue in this power and duration length, duration range. Here you see the lifetime of the different options here. Longest lifetime have flywheels. All the mechanical parts have usually a quite long lifetime. The chemical part have a bit shorter lifetime. Also, energy efficiency is highest at the capacitors and flywheels. Pumped hydro, as I mentioned already, so from 70 to 80%. Compressed air is usually significantly lower. These are the costs here. So first you have the capital costs, investments. You said here what much you pay for the battery, but here it's also considering the lifetime and cycles and the conversion efficiencies. And here you see the options of pumped hydro is here still the best. This is an overview of all technology. I load up the PDF file for you because maybe it's hardly visible on that video, but just to show you the structure of this graph here. So you have here the different technologies, starting one with pumped hydropower, going to 8 number redox flow batteries, and then you have the relative costs of that technologies, the costs per cycle, the response time, the major maturity. So this is very high here because it's been long for a very long time. So here you see the maturity of that technology. This for lithium, for pumped hydropower, this is very mature. Some other technologies, for example, here, if you take a look at lithium-ion batteries, it's semi-mature, so not completely new, but not completely mature as stationary big batteries and so on. And then you have the conversion efficiency as a parameter, the daily self-discharge, and just in a nutshell, the summary of that technology. And then you have here the different application. So where is the storage needed in the grid or transport and so on. And here you see the different dots here. This is one means just seasonal storage. Here you can use either pumped hydro storage or number 5 hydrogen storage and so on. So you can take a close look at that. Finally, I give you some hints on literature and resources. Quite extensive books, a Handbook of Energy Storage by Mr. Sterner and Mr. Stadler here. It's a new edition from 2019. The hints I gave you for the lithium-ion operation, this was from a presentation by Mr. CAES from the University of Aachen here, and you can find it under this link. This is a PDF file of that talk. There are also some other of the different technologies, some other books. Some of them are a bit older, either lead-acid batteries or supercaps and so on. You find here in this literature review here. So that's it. Thank you very much. There is now just an exercise here. And we'll discuss just quickly the exercise to be made until the next lecture. So here first exercise is here. You should compare different storage technologies. So first you have a household in the tropics that has the following consumption during nighttime. So you have here a refrigerator of 50 watts that runs permanently, so 24 hours a day. The LED lights of 4 watt each, about 10 pieces, and they run from 6 p.m. until midnight. A TV set of 150 watt power. It runs here for a telenovela from 8 p.m. to 11 p.m. and you should first find out which option is the cheapest if we compare to different battery technologies or two different battery types, the same technology. First, we take a cheap automotive battery that's available for €150, and it has 12 volt and 150 ampere hours. If you would discharge 100%, we just only consider a discharge of 50%, otherwise lifetime would be really very short. And so we consider 50% of depth of discharge. This would have a lifetime of 1000 cycles. If we go to 70% of the depth of discharge, we only have 500 cycles. Output voltage is 12 volts. Charging voltage is 13.5 volts. And then the so-called Coulomb efficiency, or other words, ampere hour efficiency, is 0.9. As a hint, this is not the energy efficiency. Second option, we would compose industrial battery. We only buy 2 volt cells and interconnect them on your own. So a 2 volt cell is available in blocks of 200 to 1000 ampere hours, and it costs €200 per kilowatt hour. It has a lifetime of 3000 cycles at 50% depth of discharge, and a lifetime of 2000 cycles at 70% depth of discharge. The output voltage is 2 volt. The charging voltage is 2.4 volts. Also, the ampere hour efficiency or Coulomb efficiency is 0.9. So if we should consider that's not the energy efficiency. So how much does 1 kilowatt hour in a storage cycle energy costs? And in total, including a PV generation, costs of 10 cents per kilowatt hour. For costs, we use the abbreviation small, so specific cost small k, for absolute costs big K. Here the small specific cost of PV is K with an index of PV. It's 10 cents per kilowatt hour. So part 2, now we equip that refrigerator with some phase change material, for example ice and so on, so we can use this ice as a thermal storage, and so we don't have to power it at nighttime because it stays alone at the low temperature, at least until all the ice has been melted. And this allows that the temperature stays at the desired temperature during nighttime. And during the day, the refrigerator and the PCM are usually operated directly by PV at costs of also 10 cents per kilowatt hour. The charging and discharging of the PVM in a cycle has an efficiency of 60% in total. So the question is, how much is the maximum price of the PCM equipment in order to be still competitive with the cheapest battery option? Lifetime of the PCM system is estimated to be 10,000 cycles. If you would have just ice, and there's no limit of 10,000 cycles, but some of the materials, the PCM materials, they are paraffins and they have a certain limit in lifetime. Okay, that's already a solution we discuss later then. Thank you very much. And this is a kind of double lecture and so on. Also, this exercise is also quite extensive. So take your time and try to solve these